Hello and welcome to the next lecture in this pattern recognition course. We have been looking at certain issues of statistical learning theory, some simple introduction to basic issues of statistical learning theory. Specifically, we have been looking at the issue of consistency of empirical risk minimization. This most algorithms which are essentially based on minimizing empirical risk, if they find global minimizer of empirical risk, will that be a good enough classifier to learn? Right? Will the global minimizer of empirical risk be same as the global minimizer of true risk? Right? That is the consistency of empirical risk minimization that we have been considering. So, specifically, we have seen that empirical risk minimization is consistent if the law of large numbers convergence is uniform over H. Recall that H is the family of classifiers over which we are minimizing the empirical risk. Given any one function H, little h, we know the empirical risk R hat and H is nothing but a sample mean estimate obtained on the sample of the training examples of the true risk. Right? Hence, for any given H, law of large numbers ensures, law of large numbers guarantees that R hat and H converges to R H as n tends to infinity. So, the issue is that is the convergence uniform over the family H, right. We see in last class that empirical risk minimization is consistent if this convergence is uniform. Okay. So, essentially then what we want is to characterize the families H, characterize the family of functions, what should the family of classifiers H should satisfy, so that such a uniform convergence holds. Right? That is the discussion that we are going to continue in this class. Recall that we are doing all this only for 2 class classification problems. Right? The others, what we are doing here, math becomes much more complicated if we consider real valued functions. So, simply taking H to be a family of binary valued functions defined over our feature space X, and for that class we are asked the question what should the family of classifiers satisfy, so that the needed uniform convergence holds. Okay. So, since this is mathematically involved, let us once again review our notation and a few things that we proved last class. So, let us start. How are we specifying our learning problem? We are given script X, which is our input space. So, for the pattern recognition problem is the feature space, all the feature vectors belong to X. So, normally it is a d-dimensional Euclidean space for us. Y is the output space, that is the set of class labels for us, and in this particular case is binary. We can take 0 1 plus 1 minus 1, it really does not matter, we are taking 0 1. Then the space of functions or classifiers over which we search is been given the symbol script H, we call it the hypothesis space. In general, the hypothesis space consists of functions that map X to another set called A, the action space. This is so that learning directly binary valued classifier functions or discipline functions, all of them can be viewed in the same framework. That is the reason why we had this H. But for the purpose of this class, where we are looking at when the family H is such that the convergence under law of large numbers is uniform, we are only considering binary valued functions. So, actually y is 0 1 and our A is equal to y. Okay. Then the training data we are given is tuples xi yi, there are n training examples, they are drawn IID according to some distribution on X cross Y. As we said already, in this framework there is no target concept. So, examples come like this, so that any noise in examples, for example, the same X can have different Y with different probabilities, right. For example, when the class conditional densities overlap, all such things are taken care of by taking this distribution to be some unknown distribution on X cross Y. Okay. We are also given what is called a loss function, right. A loss function maps y cross A to R plus, that is positive real line. The idea is L of y comma h of x as tells me the loss I suffer with the function h on a random sample x y. h of x is what the function will say on x, and y is in a statistical sense the true thing to say. So, L of y comma h of x is my loss. I still kept the more general definition of loss function. As I said, for the purpose of this class discussion, this a is y. Then we define the risk function, which assigns a number to every classifier. Given a classifier h, the risk of h is the expectation of the loss. That is, you take average of L y h x over all x and y, where the average is with respect to the same distribution with the examples are drawn. So, that is our entire issue of having representative samples. Our samples are drawn with respect to some distribution p x y, and I know how the loss is actually calculated, and ultimately I am evaluating each classifier by taking expectation with respect to the same distribution with which examples are drawn. So, risk of h, risk is expectation of loss, where expectation with respect to dpxy. So, given this, our objective is the global minimizer of risk. So, we given it the symbol h star is the value of little h that will globally minimize R h, right. So, ultimately our goal of learning is finding the function h star, which is the global minimizer of risk, right. Of course, as I said, h star may not be unique, there might be more than one function that achieves global minimum of risk, but that does not make any difference to us, because we are going to distinguish different functions in h only in terms of their risk values. So, if two different functions are the same risk value, as far as you are concerned, they are the same function. So, the fact that the global minimizer may not be unique is of no consequence to us. But the problem is that we cannot directly minimize R. Why cannot directly minimize R? Because given a h, we can't even calculate R of h, because that depends on the unknown probability distribution. Okay. So, since risk for a given h can't even be calculated, we cannot directly minimize R. So, what we decided is we have a empirical risk function, which also assigns a number to every classifier like this. This is the average of L y I h x I, average taken over all the training samples. So, essentially risk is the expectation of L y h x I. So, this L y h x I can be thought of as a random variable, is a function of the random variable x comma y or random vector x comma y. So, if I want its expectation, if I do not know the distribution, I can always approximate the sample mean. So, I get samples x I by I, calculate the value of this function and take the average, and that is what the empirical risk is. So, empirical risk is nothing but the sample mean estimator of the expectation of loss obtained through n IID samples. Okay. Since x I, y are the given samples and we know L, given any h, I can calculate R hat n, and hence in principle I can find a h where this is minimized, right. So, let us call that h hat star n. Okay. As I already explained to you, while the notation may look cumbersome, basically the hat denotes that it is an estimate of h star, the actual global minimizer, and n denotes that the estimate is obtained through a sample of n IID examples. Okay. So, an algorithm, all learning algorithms are essentially minimize empirical risk using some optimization technique. And the algorithm learns h hat star n by minimizing the empirical risk. Okay. So, this is the setup that we have, and what is it that we want for consistency? We like the algorithm to satisfy the following: given any epsilon delta, there should be some n, that is the bound and the number of examples, such that probability R of h hat star n minus R h star, the absolute difference between them being greater than epsilon, is less than delta if n is greater than capital N. R h hat star n is the true risk of what I learnt. H hat star n is the minimizer of the empirical risk, that is what I have learnt. R of h hat star n is the true risk of what I have learnt. R h star is the true risk of the optimal classifier, right. Really, as I said, h star may be not unique, but R h star is unique in the sense of the global minimizer. So, R h star stands for the global minimum of risk. So, I want the risk of what I learnt should be close to the global minimum of risk. Okay. This will tell me that h hat star n is good enough, because we HR star n being close to H star is simply that their risk values are close. This is what I want. As you seen, we also would like to have R hat n of HR star n close to R of H star, not only R of HR star n, but even R hat n of HR star n being close to R H star, because this way after I finish my learning I know H hat star n and I can calculate R hat n of HR star n. So, if this is also there, then we will know the true risk, or at least approximately know the true risk of what we have learnt. This is the issue of consistency of empirical risk minimization, and as we saw last class, both these will hold if R hat and H converges in probability to R of H uniformly over H. Right? What do I mean that? See, R hat and H is the sample mean estimator of RH. RH is the expectation of loss, R hat and H is the sample mean of loss or the IID samples. So, anyway we know R hat and H converges to RH for each individual H as n tends to infinity, but what we want is that this convergence should be uniform. That is, given an epsilon delta, there exists one capital N which can depend on epsilon and delta, such that for all H, so the supremum of the difference between R hat and H minus RH over all H greater than epsilon is less than delta if the number of examples is greater than capital N. What it means is, given an epsilon delta, I can calculate one number capital N epsilon delta which works for all H. Works for all H meaning no matter which H for which I am estimating the risk, if I estimate with this number of n samples, I will get to an epsilon accuracy. Right? So, that is what is meant by uniform convergence. Right? We discussed this last class. Now, we showed last class that uniform convergence of R hat and H to RH is sufficient for consistency of empirical discrimination. We showed that if R hat and H converges uniformly to RH, uniformly over the class of classifiers H in which empirical risk is minimized, then both these things that we wanted earlier, right, both these are satisfied. Right. So, in that sense, the uniform convergence is sufficient for consistency of empirical discrimination. We also mentioned that uniform convergence is also necessary for empirical discrimination. Right. We did not prove that, but we told that it is also necessary. Hence, empirical discrimination is consistent if and only if the class of classifiers H that we choose to minimize empirical risk over is such that the R hat and H converges to RH uniformly over this class. Okay. So, now our question is how to decide, given a H, whether or not this uniform convergence holds. Okay. Now, for that we first looked at finite H. So, basically if the class of classifiers H is finite, then uniform convergence always holds. So, the idea is that for uniform convergence, the supremum over this of R hat and H minus RH greater than epsilon should be less than delta. For if I take one capital N, that capital N should work for all H. Now, for every H, because the law of large numbers, there would be a capital N, may be dependent on H, right? But if there are only finitely many H's, I can take the maximum of all those N's. So, this will always work, right? That is the whole idea of why if H is finite, then uniform convergence always holds. In specifically, if H is H1, H2, Hm, then using the so called two-sided Hovdig bound, we showed last class the probability supremum over H belonging to script H, absolute value of R hat and H minus RH greater than epsilon, this probability is bounded above by 2m exponential minus 2n epsilon square. Matter of fact, Hovdig bound tells us that for each H, R hat and H, which is the sample mean estimator, and RH with the expectation. So, the sample mean minus expectation being greater than epsilon, that can be bounded above by exponential minus 2n epsilon square. That is what the Hovdig bound is. If there are m functions, then as you see in using a union bound, it simply adds a factor of m on the right hand side. Now, this shows that this probability will go to 0 as n tends to infinity, because as n tends to infinity this factor goes to 0, which means that if I take n sufficiently large, no matter how large m may be, if small n is sufficiently large, then this exponentially decaying term will ultimately make the right hand side less than any delta we want, and hence if we take n sufficiently large, we can make right hand side as small as you want, and hence the needed uniform convergence holds. We can make probability supremum h belong to h r hat and h minus r h greater than epsilon to be less than delta for any given delta for a particular n which is dependent on epsilon delta, because essentially I want this to be less than delta. So, I have to calculate n. So, that n can only depend on delta epsilon, right. M is a constant anyway, right. So, if h is finite, then uniform convergence always holds. Now, how do we tackle the infinite h case? So, as we very briefly discussed towards the end of last class, our main insight for tackling the infinite h case is the following. If I take any two functions h1, h2 in my bag of classifiers, their functions are such that h1 xi is equal to h2 xi for all xi in the training set, right. They take the same values on the training set. Then r hat and h1 is equal to r hat and h2, right. So, essentially what it means is that just using empirical risk over the n sample, I cannot distinguish among all possible functions in H. There will be many functions which may take the same values on the specific training examples, in which case r hat and h1 will be equal to r hat and h2, right. So, based on empirical risk, I cannot distinguish all functions. How many can I distinguish? I have got n samples and h's are all binary valued functions. So, any given h, if I look at all possible values it can take on the n sample, it is one n bit binary number, right. Every h, if I look at all possible values it can take on the entire set of training data. So, if it is the total number of n bit binary numbers. So, there can at most be 2 power n different functions that can be distinguished, because given n samples there are only 2 power n different possible binary tuples that the n example that the function the n examples can take. Means given n training examples, as far as empirical risk is concerned, we can distinguish at most 2 power n functions from h, right. So, which means we can use the same arguments as in the finite h case to tackle the general case, because we are ultimately looking at only empirical risk, and empirical risk can distinguish only among finitely many functions. So, even though the supremum over all the infinitely many functions in h, because r hat and h can take only finite can distinguish only among finitely many functions, we should be able to employ the argument that we use for finite h case. Okay. So, this is what we are going to do. So, let us particularize this argument. Okay. So, we will use a very clever combinatorial argument which was first used by Vaptek and Chervonenkis, which is called the symmetrization argument. Okay. So, the basic idea is the following. Suppose we have 2 n examples instead of n examples. Okay. Given any h belong to h, suppose we want an n sample estimate of r h, we want a r hat and h. So, we want to estimate the expectation of loss using a sample of n IID examples, but we have 2 n examples. Hence, I can get 2 estimates. I can get one estimate using the first half and one estimate using the second half of the examples, right. So, let us give some names to the 2 estimates. Let us call the estimate obtained through the first half, that is I is equal to 1 to n as r hat and h, and for I is equal to n plus 1 to 2 n as r hat and prime h, right. So, we have 2 estimates, both are n sample estimates, one is r hat n, one is r hat prime n. Okay. This is obtained over the first n, this is obtained over the second n. Okay. Now, the basic idea of the symmetrization argument is the following. Since the examples are IID, we expect the accuracy of the 2 estimates to be about the same, right, because both are obtained through n IID examples. So, it is like saying I toss the coin 10 times and find the estimate of heads using 10 samples. I toss it again 10 times and find another estimate. We do not really expect the accuracy of the estimates to be vastly different, because both of them are obtained based on 10 tosses. So, when the examples are IID, we can expect the accuracy of the 2 estimates r hat and h and r hat prime and h would be about the same. Now, what does this mean? So, the probability of their differing from their two values are both the same. So, either both of them are bad or both of them are good, so to say, which means if both of them are good, both of them are close to RH and hence they are close to each other. Right. Conversely, if they are very far from each other, then we also expect that the estimates are far from the true values, right, because they are not really good estimates. The estimate is good, then r hat n and r hat n prime n should be about the same, right. If both of them are close to RH, they should also be close to each other. Conversely, if they are far away from each other, then any one of them is likely to be far away from RH, right. This is of course very hand waving intuitive argument, but I hope the basic idea is clear, because examples are IID, whether I estimate an n sample estimate using one sample of n or another sample of n, probabilistically I should get about the same accuracy. Now, this argument can be made very precise and rigorous combinatorially, and thus we can prove this. We can show that if I want probability supreme over all h, r h minus r hat and h greater than epsilon, that can be bounded above by twice the probability of r hat n h minus r hat prime n h greater than epsilon by 2. Essentially, the idea is that if r hat n and r hat prime n is both epsilon close to r h, then they can't differ by more than 2 epsilon. Okay. Similarly, if they are farther away than epsilon by 2, then it is possible for r h minus r hat n h to be greater than epsilon. Okay. While we are not proving it, because the proof is a little involved, I hope the basic idea of this inequality is fine. This is called the symmetrization argument. So, okay, this is the probability that we want to bound ultimately, supreme over h belong to h, r h minus r hat prime n h. We want to show that as n goes large, this can be made less than any delta that we want, right. Now, we can bound this probability by this probability. What is the point? The point is here, even though r hat n h distinguishes between only finitely many h's, r h can distinguish between all h. So, this supremum directly I cannot argue that it has to be taken only over finitely many h. But here I have only 2n samples totally, r hat n h and r hat prime n h both are functions of only 2n samples. So, given 2n samples, there are only finitely many h's that can be distinguished. Right. For the rest of them, r hat n h is equal to r hat prime n h. Right. So, this difference will anyway be 0. So, to find the supremum, I need to find it over only finitely many h's. So, using this symmetrization argument, this supremum, which I do not know how to bound, is being converted into probability over another supremum, which supremum can be taken over only finitely many samples, because r hat n h and r hat prime n h, both of them are calculated from 2n samples. So, if I take any h1 h2 which take the same values on the 2n samples, then both r hat n h and r hat prime n h will be same, so to say. So, essentially one can argue that there cannot be more than finitely many h's over which the supremum needs to be taken. Okay. So, that is the basic idea. This allows us to use the procedure that we adopted for finite h case to bound the LHS in the inequality, because this can be bounded using only finitely h cases. Once I bound this, I have bound this. This is what I am interested, and I have bounded that above by this. Now, this can be bounded using only the supreme over finitely many h. So, let us go on and see how I can do that. So, if I can bound supremum h belong to h, r hat n h minus r hat prime n h greater than epsilon by 2, then I can bound the probability I want. This is the probability I want to bound. Now, because of this, if I can bound this probability, I can bound this probability, right. So, this is what we want to bound, and as I explained in the above, we need to consider only finitely many h for supremum, because this depends only on the empirical risk. Okay. So, that is the approach we want to follow. Let us ask how to make it rigorous. How do I mean taking supremum over finitely many, which finitely many, how do I know exactly how many functions I have to take the supremum over, all that. Okay. So, to go there, first let us consider any one h belonging to h. Okay. Let us give a name Zi to L y I h x i. Right? Zi is some random variable, essentially the function of x I y I. So, I am just denoting L y I h x I by the symbol Zi. Okay. So, where x I y I is a example. Note that Zi are IID because examples are IID. Let expectation Z be their expectation. Okay. That will be the risk of h. So, using this new Zi, r hat n h minus r hat n prime h is nothing but 1 by n I is equal to 1 to n Zi minus 1 by n I is equal to n plus 1 to 2 n Zi. So, essentially we have some random variable Z, right, which is L y comma h x. We have IID realizations of Z, Z1, Z2, Z2n. I am finding the mean of Z first using the first half of the samples, next using the second half of the samples. I want to know how to bound the probability that this difference is less than some epsilon. Okay. Now, how do I do this? I can use simple triangle inequality. Okay. Remember that we are considering a single h here. So, we are not at getting into supremum. So, there is one random variable Zi here, or rather IID random variable Zi, all of them are IID here. Now, so this is what I want to bound. So, I can absolute value of a minus b can be written as a minus c plus c minus b, which is then bounded above by a absolute value of a minus c plus absolute value of c minus b. So, I have just added and subtract expect value of Z. Why is this a nice idea? Because Zi or IID realizations are Z and this is the sample mean and this is the two expectation. I know how to bound this using law of large numbers, for example, Hovering inequality. This also same, and both of them are essentially have the same distribution, right, because this is a sample mean estimate of the unknown mean using n sample, this sample mean estimate of the unknown mean using n samples. So, the probability distribution of this and this is the unfold probability distribution of Zi. Okay. Now, I know how to bound each of these terms. We have already seen that using Hovering inequality. So, because this is less than or equal to this plus this, we have used this argument already more than once earlier. So, for this to be the probability of this greater than being epsilon is bounded above by this greater than epsilon by 4 and this greater than epsilon by 4. Actually, we can make it better than that because these two are essentially the same random variable, but let us just use the argument that we used earlier. So, twice the probability that both of them are greater than epsilon by 4 is a bound for the probability that this is greater than epsilon by 2, right. The actual nitty-gritty of this argument we have seen in the last class. So, as I told you, we will use this argument again and again. As I said, actually this 2 is not needed really. It is not needed because we can use what are known as Chernow bounds because both of them are exactly identical things. This is mean minus n sample estimate of sample mean. Okay. So, but because I already shown you one argument of how to do this, we will stick to that argument. I will just put it 2 because these factors do not make any difference to us. So, we know that this greater than epsilon by 2 can be bound above by twice probability this greater than epsilon by 4. And this we know how to bound, right. Zi refers to only one h and using law of large numbers and the Hovering bound, we can bound this, right. What is that bound? Hovering bound tells us that the sample mean minus expectation greater than something is less than 2 exponential minus n times that something square. So, I get epsilon squared by 16 and the 2 in the numerator cancels 1. So, I get 2 exponential minus n epsilon squared by 8. This is the same Hovering bound we used earlier. Okay. So, note that Zi is L of y h x I for a specific h Hence, 1 by n is equal to 1 to n z I is the r hat n for that h, expectation z is r h. So, what we have shown is r hat n h minus r h greater than epsilon by 4 is less than or equal to exponential minus n epsilon square by 8. This we know from Hopting bound. Right. So, going back, what is this for? Originally, this is what we want. This is r hat n h, this is r hat n prime h greater than epsilon by 2 I want. That is twice the probability of r hat n h minus r h greater than epsilon by 4. This we bound using Hopting bound like this, right. And hence, the original one r hat n h minus r hat n prime h greater than epsilon by 2 is twice this probability, it becomes 4 exponential minus n epsilon square by 8. Right. Now, this is for a specific h, right. For any given h, this is true, but the bound is independent of h, it does not depend on h, the right hand side does not depend on h, because it does not depend on h, the same bound holds for any h, no matter what h I want, I can use the same bound. So, if I change the h on the left hand side, I do not have to change the bound here, which means like in our finite case, if we take supremum in the left hand side probability over m functions, then we get a multiplicative factor of m here, right, that is what we did earlier. So, essentially if I am taking supremum over h for or some m different functions h here, then this simply becomes 4 m exponential minus n epsilon square by 8. Okay. So, let us go over this argument again. The probability that we actually want to bound is this, right. What we bounded is for a particular h, but with a bound that is independent of h, but we actually want to bound is this. We also know that because these are r hat n's, given sample of 2 n data, we need consider only finitely many h while dealing with them, right. While dealing with this term, I need to consider only finitely many h. So, I can take the supremum of finitely many h, and when I take supremum of finitely many h, I think that I can put that finite number on the right hand side, okay. And supremum need to be taken over only finitely many h. The real catch, everything is so far looks very nice. So, basically it looks like I have for one h I have this, right, and I want the supremum, and supremum need to be taken only finitely many things. So, I can just use that bound and put that number there. Of course, obviously things can't be that simple. The catch is the following: this actual number of such h depends on the specific random sample of examples we have. In that sense, that number is a random variable, right, because it depends on what are the specific xi that I have drawn in this 2n sample. So, if S2n denotes a sample of 2n examples, then this number of function that we need to consider has to be written as a function of h, 2n and S2n, right. This function obviously depends on what is the maximum number of functions I need to consider for the supremum. Very much depends on what functions are there in h, right. So, it is a function of h certainly. It of course depends on number of samples, but in addition to that, it also depends on the specific examples we have, right. So, I can directly use this number on the right hand side for this probability bound, because it is a random variable. Okay. What do I do about that? What I do about that is okay, the number of distinguishable functions in h, distinguishable based on a sample of 2n examples, which now we are given this symbol m of h 2n s 2n, is random because it is a function of the specific 2n samples. What it means is, if I can consider a particular 2n sample, then it is a given number, right. That is what it means. For any given particular sample of 2n, it is a specific number, but a sample of 2n examples is a random variable, random vector, and hence this number is also a random vector. Meaning, if I can condition my probabilities on a specific sample of 2n, then I can use this number, right. So, we can certainly write now supremum h belonging to h r hat n h minus r hat n prime h greater than epsilon by 2 conditioned on the random variable S2n will be less than or equal to 4 times this number now, m h 2n S2n exponential minus n epsilon square by 8. Earlier we shown that for any one h, r hat n h minus r hat n prime h greater than epsilon by 2 is bounded above by 4 times exponential minus n epsilon square by 8. Now, given a particular sample of 2n examples, the random variable vector S2n, we know there are this many distinguishable functions for the supremum. So, now the supremum probability is bounded above by this number. Of course, this is nice as far as it goes, but this is not the probability we want to bound, right. This probability we do not want to depend on the sample, right. So, we want the unconditional probability here, not conditioned on S2n, but we now know how to bound this probability conditioned on S2n. So, can I somehow use the bound on the probability of the supremum being greater than epsilon by 2 conditioned on S2n to find a bound on the probability that the supremum is unconditional probability that the supremum is greater than supremum, the difference between these two is greater than epsilon by 2. Okay. So, this is the next question. We can do it using some standard probability tricks. The trick is like this: given any event A, let A be any event, and let I subscript A be the indicator function. I A is 1 if A has occurred at 0 otherwise. So, this is how events can be converted into random variables, and let X be any other general random variable. Right? How it related to A is of no consequence to us right now. Then we already seen some properties of conditional expectation. So, probability of A is expected value phi of A, right. The indicator random variable takes only 2 values 1 and 0. So, expectation of a binary random variable, the probability takes value 1, and indicator random variable is 1 whenever A occurs. So, expected value of phi of A is probability of A, that all of us know, and we know expectation is expectation of conditional expectation. So, expectation of phi A can be written as expectation of phi A given X. The outer expectation is with respect to distribution of X, because the inner conditional expectation returns a random variable that is a function of X. So, the outer expectation is with respect to distribution of X. So, I can write this like this. So, I am taking the outer expectation, there is an expectation integral with respect to the distribution of X of the function inside the expected value of I A given X. Now, I A is still a binary random variable. So, expectation binary random variable is still its probability. So, this is nothing but probability A given X dpx. In a sense, this is a generalization of the standard sum rule we have in probability. We can always write if B1, B2, B3 is a partition of omega, then probability A can be written as probability A given B1 into PB1 plus probability A given B2 into PB2 plus probability A given B3 into PB3, right. This I can do for any finite partition. Essentially, conditioning on random variable says that this rule, this total probability law as it is called, can be extended to an uncountable summation also by using conditioning on random variables. Okay. So, coming back, if I have any event and I know the probability of the event conditioned on some random variable, right, then by taking expectation of this with respect to that random variable distribution, I can get the unconditional probability of A. That we can use now. We want probability of this event. We know the probability of this event conditioned on the random variable S2n. So, I can write the unconditional probability of this event at the probability of the same thing conditioned on S2n into dp S2n integral. So, it is an expectation integral of S2n. Now, this term, this probability supremum r hat n minus r hat prime and greater than epsilon by 2 condition on S2n, we have a bound for this, right. We have a bound for the probability that is inside this integral, right. So, we can substitute that bound. If I substitute that bound, what will I get? So, this is what we have. So, this probability is equal to this, but this probability is less than or equal to something else. So, by putting that, this probability is less than or equal to, this is the bound we had, right. This is the bound we had earlier. So, we substituted that bound. Now, what is this integral? 4 times exponential minus n epsilon square by 8 will come out of the integral, because that does not depend on S2n. So, what I am left with is m of h comma 2n comma s 2n into dp s 2n integral. Now, m h 2n s 2n is a random variable that is a function of s 2n, it is like some g of s 2n. So, if I take g of s 2n into density of s 2n integral, that will give me the expected value of that. So, the integral on the RHS is nothing but 4 times exponential minus n epsilon square by 8 into expected value of m h 2n s 2n, where the expectation is with respect to the various s 2n's, right. S 2n is the random thing, is various 2n samples I can get, right. So, now I got a proper bond. This can be bounded above by 4 times exponential minus n epsilon square 8 multiplied by expected value of m h 2n s 2n, where m h 2n s 2n is the number of distinguishable functions based on distinguishable functions h based on a sample of length 2n, where the sample happens to be specifically s 2n. Okay. Am I done? This is the probability. If I bound this probability, I can bound the other probability I am interested in. This probability now are bounded. Am I done? Unfortunately, I am not done, because I do not know expected value of m h 2n s 2n. Of course, I do not know m h 2n s 2n anyway, but a given s 2n also I do not know, I have not told you how to calculate. The expectation anyway I cannot do, because I cannot take the expectation equal s 2n, because that involves the probability distribution with which x and y come. But what we can do is we can approximate the expectation, we can bound the expectation itself by the maximum of m h comma 2n s 2n, where the maximum is taken over all possible samples s 2n. The expectation always of any random variable has to be less than or equal to the maximum value that random variable takes, and hence this expectation can always be bounded above by the maximum over s 2n of m h 2n s 2n. Because I really do not know at this point of time how to calculate this, and hence I do not know how to calculate this, but we will tell you later on that calculating this is not that difficult, right. Not that difficult means there are ways to conceptualize this calculation. So, if for any given 2n sample I know how to calculate this, then I can calculate, or if I can somehow find the maximum possible, right, then I am done. I do not need the distributions, I do not need the expected value. Okay. So, let us say it is of course an abjure notation, but we will say max of m h m s m for any integer m, we write it as m h comma m. Of course, m is originally given as a function with 3 variable arguments, now I am calling it a 2 argument function, but this kind of abjure notation is often done. So, we will write m of h comma m little m as max over all possible m length samples of the number of distinguishable m length samples for any particular sample. Okay. So, this denotes the maximum number of functions to consider if we have m examples, right. So, with one specific m sample, there may be some number of maximum functions to consider. With another specific m sample, there might be some other number of functions that we need to consider to take the supremum. We are saying over all possible m tuples of examples we could draw, what is the maximum number of distinguishable functions? That is what this is. We can certainly bound this above by that. So, that is what we call m of hm. Okay. So, now we can use all this to get a bound on the probability of interest, right. See, this is what we started with. We want to get supremum h belong to h, r hat n h minus r h greater than epsilon, because we want to know whether r hat n converges to r uniformly over h. Using symmetrization argument, we can bound this by twice the probability that r hat n h minus r hat n prime h greater than epsilon by 2, where these are sample mean estimate is empirical risk or the sample mean estimate is obtained on a 2n sample using the first n and the second n. Now, with what we have done so far, this in turn can be bounded above by 8 exponential minus n epsilon square by 8 m times h comma 2n, okay, where m h comma 2n, because this is based on, these are calculated based on 2n samples, I have to put 2n there. M h comma 2n is the maximum number of distinguishable functions in h over all possible samples of length 2n. Okay. So, this is our final bound now. Okay. So, let us write this bound. So, this mh2n I want to push it under this expectation. So, under this exponential. So, I can always write it as e to the power ln mh2n. So, then it comes into this exponential function. So, by doing that I can write this bound as 8 exponential minus n epsilon square by 8 plus ln mh comma 2n. Is this a good enough bound? Will it let me show that this probability can be made as small as I want by taking n as large as I want? Is this good enough? Well, is good enough or not depends on how this number grows. This is the log of the maximum possible number of distinguishable functions based on 2n samples. So, we want to know this number obviously depends on this 2n and hence obviously depends on m. So, for a given m, we want to know how ln m h comma m grows with m. If the logarithm of capital M grows linearly with m, then this bound is not useful at all, right. If this logarithmic term grows linearly with 2n or linearly with n, then this we have inside the exponent we have two terms, one term linearly decreases with n, another term linearly increases with n. So, we cannot say that this can be made as small as you want by taking n sufficiently large. On the other hand, if this grows less than linearly with n, let us say it grows only logarithmically with n, then we are done, because this falls off linearly as n, this grows only logarithmically as n, and hence the RHS can be made as small as we want. So, whether or not this bound is useful in the sense whether or not with this bound we can show that this probability can be made less than delta, depends on how ln m h comma m in general or ln m h comma 2n will grow with the number of samples. Okay. So, everything now hinges on how this function grows with n. Okay. So, here is another great result which unfortunately we will not be able to prove. So, let us give a name for this thing, let us call g h of m to be this logarithm of the number of distinguishable functions from h over all possible m samples, right. Let us call that g h of m. Okay. It only depends h and m. So, I put h as subscript and m as the main argument. In a very seminal paper in 70s, Wapnick and Chervonenkis showed that for any family h, there is a number which we call d subscript v c of h, which may be infinite, that is why I said less than or equal to infinity, such that as long as m is less than or equal to d v c of h, g h m grows linearly in m ln 2. Basically, what it means is the capital M itself grows as 2 power m. That is why ln of that will become m ln 2. We already know that given m samples, the maximum possible distinguishable things on any m sample is 2 power m. So, what this result shows is, of course, in the beginning, the maximum distinguishable number of functions grows as 2 power m as the intuition says. So, till some number which we call dBCH, till m reaches the dBCH, GHM grows linearly or capital M grows as 2 power m. But after reaching the size dVCH, the GHM, this is ln of capital M, will grow only logarithmically in m. Okay. The actual growth is dVCH into ln m by dVCH plus 1, but the growth is logarithm, which means capital M will grow only as linearly in m. So, this dVC of h is called the VC dimension of h, because a number that we associate with h is called the VC dimension of h. So, what this says is that if the VC dimension is less than infinity, then we have a proper bound, because there is some number which we call dVC of h. After that, this ln will not grow linearly, right. So, after some n which is determined by the dVC of h, this number will not grow linearly, and hence whether this is falling off linearly, this will grow only logarithmically, and hence this can be made less than delta. So, if the VC dimension of H is less than infinity, then we have a proper bound and consistency theorem is assured. Okay. We still haven't come back to define this, but we'll see at the VC dimension of H in next class much more detail. But all it says is given any H, there is some number which we call the VC dimension of H, and the number of distinguishable functions grows exponentially only till as long as the sample size is less than VC dimension of H. After that, it does not grow exponentially. Okay. So, m h comma m is the maximum number of distinguishable functions based on all possible sets of m IID examples. So, what we have is that this maximum possible number, we know the real maximum is 2 power m, it stays as 2 power m till m reaches dVc of h. After m reaches dVc of h, the growth is linear, and this means because the growth is linear, we can bound the generalization error. Okay. Of course, so if dVc h is less than infinity, we can bound. dVc h is equal to infinity, we cannot bound by our method, but we do not know whether there is any other bound, but one can show that if dVc h is infinity, VC dimension of h is infinity, then we cannot bound and ERM is not consistent. So, let us sum up the whole argument that we got so far. For empirical risk minimization to be effective, what we want, see we are finding the global minimizer of empirical risk, right, and we are asking how close is it to global minimizer of true risk. Now, closeness is only in terms of the true risk of a function, right. So, I am asking is the true risk of what I learn is h hat star n, the minimizer of empirical risk. Is the true risk R of h hat star n close to the global minimum possible risk, which is R h star. So, for empirical risk minimization to be effective, this is what we want. Right. We have seen that this will happen if the R hat n h, which is the sample mean estimator of the true risk based on n IID samples, converges to true risk, that is the expected value of loss, uniformly over h. We know anyway that the sample mean the mean of the expectation of loss function that we want can be obtained in the limit at the sample mean using law of large numbers, but the question we are asking is this convergence uniform over h, right, where h is the family of classifiers over which we are minimizing empirical risk. What we have now found is that the needed convergence holds if h has finite VC dimension, where what is VC dimension? So far, VC dimension for us is if m h comma m is the maximum number of distinguishable functions based on all possible sets of m IID examples, till m is less than or equal to dVc of h, this maximum stays as 2 power m, and after that it is less than 2 power m. Why should there be such a number? Because this guys have showed that is the only possible way this function, the maximum number of distinguishable functions from a family of classifiers based on m number of samples, right. That number, if you take logarithm of that number, that function has only 2 possible growth rates. It grows as m ln 2, that is capital M grows as 2 power m till some integer. After that, it grows logarithmically in m. Okay. What they showed is given any h, there is such an integer that we can associate with h, such that till that time this grows exponentially, after that it does not grow exponentially. Okay. Of course, there can be h for which there is infinite, in which case it forever grows as 2 power m. That is the reason why you cannot learn if the VC dimension is. So, this is all we have defined VC dimension to be. So, at this point of time, except that because of the Vapnik-Chenoweth result, we know it exists, we still have not really conceptualized how to calculate VC dimension given h, that we will do later on. Okay. But let us understand our summary. Empirical risk minimization to be effective, we want R h hat star n to converge to R h star. We seen that this will happen if the law of large numbers convergence of R hat n h to R h is uniform over the family h, and the uniform convergence will happen if h has finite VC dimension, right. So, hence the question now is to find the VC dimension of H. How do we find VC dimension of H? Okay. But before getting into VC dimension of H, which we will do the next class, we will very quickly take a look at what the kind of bound we obtained on the generalization error. Okay. Actually, what we will do is the following. See, we have this bound that we obtained on the generalization error. This is essentially generalization error for us. This is how many examples. See, if I need to calculate n so that this is less than delta, right, that will tell me the uniform convergence hold, that will tell me how many examples I need before r hat and h is close to r h for every h in my family, right. Now, this depends on the VC dimension. Okay. So, by looking at this bound and what we know about how this Ln MHM can go, we can actually get some interesting idea about the generalization error. Okay. So, what we will first do, this also we will do next class, is we will examine this bound so that we understand what VC dimension is giving us. VC dimension not only tells us whether or not the needed uniform convergence holds, and hence whether or not the empirical disk minimization is effective. It will also give us, as we shall see, some idea of the complexity of the learning problem. How complex is it to learn a particular H? So, what we will do next class is we will understand how this bound that we derived brings out the issue of complexity of H, and after that we will see how starting from the definition that we gave here, we can actually conceptualize a procedure for calculating VC dimension of a given set of classifiers. Then we will go back and calculate it for some of the examples we have seen earlier. Okay. Thank you.